Right now, at this exact moment, there exists something in our universe, so impossibly massive that your brain probably can't even process what you're about to hear. And I'm not exaggerating. Scientists literally had to invent new measurement scales just to describe how large it actually is. Here's what will blow your mind. There's a black hole called Ton 618, and when astronomers first measured it in 2003, they didn't just find something bigger than our sun. They didn't find something bigger than Jupiter or our entire solar system. They found something that would require 66 billion suns, 66 billion, arranged in a perfect line just to match its diameter. Think of it like this. If Earth was the size of a grain of sand, Ton 618 would be bigger than the entire observable universe. And that's not a metaphor. That's the actual scale we're dealing with. But here's what gets even crazier. Ton 618 might not even be the largest black hole we know about anymore. And the implications of something this massive existing at all will fundamentally change how you understand reality, gravity, and your place in the cosmos. Before we go deeper into this rabbit hole, I want to hear from you in the comments. Where are you watching from? What country? And what time is it where you are? I read every single comment, and I genuinely want to build a community of cosmic explorers around this channel. So drop that info below. And please, if your mind is already blown, and we're only 3 minutes in, hit that subscribe button and turn on notifications. What we're about to explore together is going to rewire how you think about space itself. This isn't just another astronomy video. This is your invitation to understand something so massive that it breaks human intuition. Let's go. Before we can understand how absolutely ridiculous Ton 618 is, we need to talk about what a black hole even is. And I promise you, even if you think you know, there's going to be something here that surprises you. A black hole is what remains when a massive star, and we're talking about a star hundreds of times heavier than our sun, reaches the end of its life and collapses. When it dies, all that matter gets crushed down into an infinitely small point called a singularity. The gravitational pull at this point becomes so intense that nothing, not even light, can escape it. Now here's what blows most people's minds. Light is the fastest thing in the universe. It travels at 186,000 miles per second. Nothing can outrun it. And yet, a black hole can trap light. That's not just heavy. That's the definition of gravity-breaking power. The edge of a black hole is called the event horizon, and this is crucial. This is the point of no return. Cross it, and you're gone forever. You can't escape. You can't send a message out. You're just done. In 1916, Albert Einstein predicted black holes using his theory of general relativity. But here's what's fascinating. Einstein himself didn't believe they actually existed. He thought they were just mathematical curiosities. It took decades of work by scientists like Roy Kerr in 1963, who figured out that rotating black holes were mathematically possible, before we realized Einstein's own math was showing us something real. And in 2019, Katie Bouman and the Event Horizon Telescope collaboration actually photographed a black hole, the first time humanity ever SAW1. That image completely shocked the world because it proved they were real. Think of a black hole like a cosmic drain. Imagine space as water, and the black hole is a whirlpool that gets stronger the closer you get. Once you're in the center of the whirlpool, there's no swimming back out. But here's what we need to understand before Ton 618 makes sense. Black holes come in different sizes. And when I say different sizes, I mean mind-bendingly different. The smallest known black holes might be formed from individual collapsed stars. The largest? Well, that's where Ton 618 comes in, and that's where things get absolutely insane. The question you should be asking right now is, how many black holes exist? And how big can they possibly get? Stay tuned, because the answer is going to shake everything you thought you knew. What if I told you that your brain is physically incapable of understanding how large ton 618 is? I'm not saying you're not smart enough. I'm saying your brain literally didn't evolve to process sizes at this scale, and that's actually fascinating. Let me prove this to you. Close your eyes for a second and visualize a million. Got it? Now visualize a billion. Feel the difference? Most people say they don't. Your brain treats them the same way as a really big number, even though a billion is 1,000 times larger than a million. Humans evolved on a planet where the biggest things we encountered were maybe a few hundred meters across. A mountain, a canyon, the horizon. Our brains got really good at understanding those scales. But when we jump to billions, millions of billions, or astronomical distances, we hit a cognitive wall. Here's the thing. Scientists deal with this problem constantly, and they developed a solution. It's called the power of analogy. Think of it like this. If our sun was the size of a golf ball, Jupiter would be the size of a marble next to it. Our entire solar system from the sun to Neptune would fit inside a football stadium. Now, the nearest star to us, Proxima Centauri, even at that scale, it would be 6,000 miles away. That's the distance from New York to London, and that's just the nearest star. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. To visualize this, if every grain of sand on every beach on Earth represented a star, that still wouldn't be enough grains to represent our galaxy. And that's just one galaxy. In 2016, astronomers used the Hubble Deep Field observations from researcher Christophe Conselles and his team to calculate that the observable universe contains approximately 2 trillion galaxies. 2 trillion, each with hundreds of billions of stars. Let that sink in. You're a conscious being on a rock floating in an infinite cosmos so vast that light itself, which can circle Earth 7 times in 1 second, takes over 4 years just to reach the next nearest star. And within this unimaginable universe, ton 618 exists. It's not the biggest thing in the universe, but it's the biggest single thing we've ever directly observed that a human could theoretically point to and say, that right there. So before we reveal what ton 618 actually is, I need to establish one more framework in your mind. We need to talk about how big black holes get. Because here's the thing that will completely mess with your head. The bigger a black hole gets, the weirder it becomes. The physics doesn't scale the way you'd think. In fact, and this is crucial, larger black holes are actually less dense at their event horizon than smaller black holes. TON 618 is so massive that you could theoretically pass through its event horizon without even noticing it. You wouldn't die getting pulled in. You'd only die once you got close to the singularity at the center. This is the kind of cosmic paradox that makes physicists lose sleep. We're about to cross a threshold from understanding black holes in general to understanding this specific black hole. And trust me, nothing prepares you for what you're about to learn. Here's a question that stumped astronomers for decades. Why do black holes come in such drastically different sizes? Why not just have one kind? For decades, scientists detected 2 categories of black holes. The first category is what we call stellar mass black holes. These form when a massive star, maybe 20 to 30 times heavier than our sun, explodes as a supernova. The core collapses, and you get a black hole maybe 10 to 20 kilometers across. That might sound small, but 20 kilometers is the distance you drive in a car for about 12 minutes on a highway. But here's what's wild. All the mass of a star that was 30 times heavier than our sun, all that gravity, all that crushing force compressed into something you could almost drive across. In the 1970s, Stephen Hawking made a mind-bending discovery. Black holes actually emit radiation. This was revolutionary because everyone thought nothing escaped black holes. But Hawking's equations showed that quantum effects near the event horizon create particle-antiparticle pairs, and sometimes one escapes while the other gets consumed, making the black hole slowly lose mass. Hawking radiation, as it's now called, was one of the most important discoveries in theoretical physics. But stellar mass black holes? They barely emit any radiation. They're stable. They're dark, cold, and isolated. Then there's the second category, supermassive black holes. And supermassive is where language starts to fail us. Every major galaxy in the universe, including our Milky Way, has a supermassive black hole at its center. Our own galaxy's black hole is called Sagittarius A*, and it's about 4 million times the mass of our Sun. It's not in our solar system. It's about 26,000 light years away at the center of our galaxy. We can't see it with our eyes, but we can detect it by watching stars orbit around it, revealing its presence through gravitational effects. Think of it like this. If our stellar mass black hole is the size of a marble, Sagittarius A* is the size of a house. Actually, that's not a good enough comparison. If a stellar mass black hole is a marble, Sagittarius A* is like a small city. But here's what blows astronomers' minds. Sagittarius A* is actually on the small side for a supermassive black hole. It's like we found out that the biggest thing in your house wasn't actually that big compared to other houses in the universe. Supermassive black holes have been measured to be as large as 20 billion times the mass of our Sun. We're talking about cosmic structures so dense, so gravity-warped, that they literally bend space and time around them. The million-dollar question became, how do supermassive black holes form? If they started from stellar mass black holes, you'd need countless collisions and mergers to reach billions of solar masses. But the universe is only 13.8 billion years old. Is there really enough time for enough collisions to happen? This question haunted cosmologists. And then TON 618 entered the picture, and everything got weirder. Some supermassive black holes seem to have grown impossibly fast in the early universe. They became massive in just a few 100 million years after the Big Bang. This suggests either we're missing something about how black holes grow, or we're missing something about supermassive black holes that formed in a different way. Or some black holes might be primordial, meaning they were created at the moment of the Big Bang itself. Each of these possibilities shakes the foundation of what we thought we understood. And TON 618? TON 618 is the most extreme example of this mystery. In the 1950s, astronomers started noticing something strange in the sky. There were these objects that looked like stars, but emitted massive amounts of radio waves. They called them quasi-stellar radio sources. Quasi-stellar, meaning kind of looks like a star. The name got shortened to QSOs, then quasars. For a while, scientists had no idea what quasars actually were. They were baffling. These objects were incredibly far away. We could tell that from the redshift, a property discovered by Edwin Hubble, and yet they were incredibly bright. Absurdly bright. Some quasars emit as much light as an entire galaxy from a region smaller than our solar system. How is that even physically possible? The answer: supermassive black holes. In 1963, Martin Schmidt, an astronomer at Caltech, measured the spectrum of a quasar and realized it was incredibly distant, way farther than anyone had expected. This meant these objects had to be ridiculously luminous to appear as bright as they did from Earth. Later, research by scientists like Reinhard Genzel and Andrea Ghez, who won the 2020 Nobel Prize for their work measuring the black hole at our galaxy's center, revealed that quasars are powered by supermassive black holes actively feeding on surrounding matter. Imagine a black hole surrounded by a disk of gas, dust, and stellar materials spiraling inward. As this material falls toward the event horizon, it heats up to millions of degrees. The friction is so intense that it emits tremendous amounts of radiation. This is called an active galactic nucleus, or AGN, and the radiation blast is so powerful that we can detect it from billions of light years away. TON 618 was first catalogued in 1957. The TON stands for Tonantzintla Observatory Night. It was identified during observations at an observatory in Mexico. It appeared as just another quasar among thousands. Astronomers had a catalog of these objects, and Ton 618 was in the catalog, but nothing special seemed to distinguish it. For decades, Ton 618 was forgotten. It was just another quasar, another bright spot in the sky. But then, in 2003, a Chinese astronomer named Zhu Bingwu used data from multiple sources, including infrared observations, to estimate the mass of the black hole powering Ton 618. His calculations suggested that the black hole at the center of Ton 618 might be around 66 billion solar masses. When that result came out, the astronomical community went quiet for a moment. 66 billion suns. Let me put that in perspective for you. Our sun's entire lifespan, from birth to death, will be about 10 billion years. In that time, all 66 billion of those suns could be born, live full lives, and die. And you still wouldn't match the mass of Ton 618's black hole. I want you to do something for me. I want you to visualize Earth. Got it? You're imagining our little blue marble, right? You can see it in your head. You probably even know roughly how big it is. About 8,000 miles in diameter. You could drive around the equator in a few months if you drove non-stop. Now imagine the sun. The sun is so massive that 1.3 million Earths could fit inside it. Imagine that. Balling up our entire planet, every ocean, every mountain, every forest, every human that's ever existed, and you could pack in 1.3 million of those Earths into the sun. Now, Ton 618's event horizon, just the event horizon, not even considering the full gravitational effects, has a diameter of about 390 billion kilometers. Let me give you that number in miles, because kilometers might not hit you the same way. 242 billion miles. The distance from Earth to the Sun is about 93 million miles. We call that distance 1 astronomical unit, or O. It's how we measure distances within our solar system. TON 618's event horizon is about 2,600 astronomical units across. Our entire solar system, every planet, every moon, every comet, the whole thing fits inside Ton 618's event horizon with room to spare. A massive amount of room to spare. Think of it like this. If the observable universe was the size of a football field, the Milky Way galaxy would be a grain of sand on that field. Our solar system would be a grain of sand on that grain of sand. And Earth would be a grain of sand on that grain of sand. TON 618's event horizon is the size of that football field. Actually, that still doesn't do it justice. Let me try again. Imagine you're standing on Earth. The sun is 93 million miles away, right? And it takes light about 8 minutes to travel from the sun to your eyes. Light is the fastest thing in existence. Now imagine instead you were standing at the edge of Ton 618's event horizon. The singularity at the center, the actual infinitely dense point where all the mass is concentrated, is about 390 billion kilometers away. Light from that singularity would take about 1,460 days to reach you. Almost 4 years. You would be inside the event horizon, and you'd have to wait 4 years to see light from the center of the black hole. The black hole is so massive that the space inside it is so warped that light takes 4 years to travel distances that it normally covers in seconds. But here's the thing that makes this even crazier. Ton 618 might not be alone. In 2011, astronomers discovered evidence of an even larger black hole. It's called Holmberg 15A, and some estimates suggest it might be as massive as 170 billion solar masses, 2.5 times bigger than Ton 618. We can't observe Holmberg 15A as directly as we can Ton 618, because it's not actively feeding and therefore not producing the intense radiation that makes quasars visible. It's a sleeping giant, dark and cold, but still there, warping space around it. The mystery deepens. The questions multiply. And in this section alone, I hope you're starting to feel that fundamental shift in your understanding, that sense that space is so much more extreme than we ever imagined. We're about to cross into the deep end of this exploration. Hold on. Here's something that keeps theoretical physicists awake at night. The laws of physics as we understand them don't work at the center of a black hole. They literally break down. We have no equation, no formula, nothing in our arsenal of mathematics that can describe what happens inside a singularity. General relativity, Einstein's masterpiece that explains gravity and the large-scale structure of the universe, predicts that all. The mass of a black hole is crushed into an infinitely dense point, infinite density, infinite gravitational curvature, a literally infinite number at the center of reality. And infinity isn't a number. It's a mathematical statement that this thing is beyond calculation. But here's what makes it worse. Quantum mechanics, the physics that rules the tiny world of atoms and subatomic particles, says something different. Quantum mechanics says you can never have infinite density because of uncertainty principles. The more you try to squeeze something into a smaller space, the more uncertain its momentum becomes, and that uncertainty actually prevents infinite density. For decades, physicists have been trying to resolve this contradiction. In the 1990s, Juan Maldacena discovered something remarkable, a deep mathematical connection between gravity and quantum mechanics through something called the holographic principle. He showed that a black hole's three-dimensional interior could be described by quantum information on its two-dimensional event horizon. It was a mind-bending revelation that suggested the universe might work like a hologram. But even with these breakthroughs, we still don't have a complete theory of quantum gravity. We don't truly understand what happens at the singularity. And TON 618 singularity? If we can't understand singularities in general, TON 618 singularity is like the ultimate puzzle. We're talking about the densest possible concentration of 66 billion suns worth of mass compressed into a point that defies comprehension. But here's something almost nobody realizes. Inside TON 618, near the event horizon, you wouldn't necessarily feel torn apart. In fact, this is one of the most counterintuitive aspects of massive black holes. Let me explain. When you get pulled into a small black hole, say, a stellar mass black hole, like one that's only 10 kilometers across, the difference in gravitational force between your head and your feet would be enormous. Your feet would experience so much more gravity than your head that you'd literally be stretched like spaghetti. Physicists call this spaghettification, and it's a terrible way to go. But TON 618, because it's so massive, the event horizon is spread out over such a huge area that the gravitational gradient, the difference in gravitational pull between different parts of your body, would be relatively gentle. You could theoretically cross the event horizon of TON 618 without immediately noticing you'd gone past the point of no return. You'd be doomed, yes, but you wouldn't immediately realize it. This is where things get philosophically weird. You could be inside TON 618's event horizon and not know it. You could be committing your last moments without knowing it. There's no alarm, no warning light, just the vast, unknowable curve of space-time bending around you, pulling you inexorably toward a singularity where physics itself fails. And we still don't understand what's at that center. We don't understand what happens when you reach it. Time itself becomes meaningless at the singularity. Or maybe time doesn't break down. Maybe our understanding of time is the problem. Maybe time is something completely different than what we think. This is the border of human knowledge. And TON 618 is standing on that border, challenging everything we think we know about reality. What happens when you feed material to TON 618? What happens when stars, gas, dust, and entire matter clouds fall into this cosmic monster? Let me paint a picture for you. TON 618 is actively feeding. It's consuming material from its surroundings, And as that material spirals inward, it heats up. We're not talking about warm. We're not even talking about the surface of the sun's temperature. We're talking about temperatures approaching hundreds of millions of degrees. At these temperatures, matter doesn't exist in any form you're familiar with. It's not solid, liquid, or gas. It's plasma, a superheated state where electrons have been ripped away from atoms. The magnetic fields generated by the spinning black hole twist this plasma into jets that shoot out in opposite directions at nearly the speed of light. These jets extend for thousands of light years. Imagine that. Matter is flowing into ton 618 at the center, and a beam of that energy shoots out for thousands of light years. You could have a jet from ton 618 that reaches from Earth and passed far beyond our nearest star, and it would still be just a tiny fraction of the jet's total length. Think of it like this. If you had a garden hose and you turned it up to maximum pressure, you might spray water 20 feet. Now imagine a hose so powerful that the spray reaches 20,000 miles. That's the power differential we're talking about. Except these aren't water jets. They're beams of pure plasma and radiation that carry as much energy as entire supernova. The radiation from ton 618's accretion disk, the disk of material spiraling in, shines as brightly as 140 trillion suns. Let me repeat that. 140 trillion suns. Our entire galaxy, the Milky Way, with its 100 to 400 billion stars, shines with the light of a few hundred billion suns combined. TON 618 is over 1,000 times brighter than our entire galaxy. A single quasar at the center of a distant galaxy shines brighter than all the billions of stars around it combined. And we can see this light from Earth. Ton 618 is so bright that despite being nearly 18 billion light years away, astronomers can detect it with telescopes. That light has been traveling toward us for 18 billion years. It left ton 618 when the universe was less than 1 billion years old, and it just now reached us. When that light left ton 618, the universe was in a different state entirely. Most of the galaxies we see today hadn't even formed yet. The cosmic structure we see now was just beginning to coalesce. And ton 618 was already there, already massive, already shining brighter than billions of suns combined. This leads us to one of the greatest mysteries in cosmology. How did ton 618 grow so large, so fast? How did something reach 66 billion solar masses in the early universe, when there might not have been enough time for that to happen through normal black hole growth? The answer involves something called runaway growth, and it's about to reframe everything you thought about the early universe. Here's the question that made cosmologists scratch their heads for years. If black holes grow by consuming material and merging with other black holes, and if each collision and feeding takes time, how did ton 618 become so massive so quickly? The universe is 13.8 billion years old. We think the Big Bang happened 13.8 billion years ago. Yet we found black holes like ton 618 that are 66 billion solar masses, and were already that massive when the universe was just 875 million years old. That means ton 618 had about 875 million years to grow, from nothing to 66 billion times the mass of our sun. Do the math. That would require ton 618 to gain mass at an absolutely insane rate. The numbers suggest that ton 618 would have to double its mass approximately once every 12 million years or less in the early universe. In 2008, Luigi Maiani and other theoretical physicists began proposing solutions to this growth problem. One possibility, maybe black hole seeds, the initial black holes that started the growth process, were much larger than we thought. Maybe instead of starting from stellar mass black holes a few hundred kilometers across, the first black holes were directly created by the Big Bang itself, already possessing millions or billions of solar masses as primordial black holes. Another possibility, maybe the early universe had much denser concentrations of matter. Maybe gravity in those early times allowed for faster growth rates that our current theories don't fully account for. A third possibility emerged. Maybe black hole growth can be triggered in stages. A black hole consumes the gas around it, creating a triggering event that causes more gas to flow in, which triggers more consumption, which triggers even more consumption. A cascade of feeding that amplifies at each stage. But here's what really blows physicists' minds. TON 618 might not even be the most extreme example of this paradox. In 2017, astronomers discovered an even more distant quasar powered by a black hole that might be just as massive as TON 618, but even further away, meaning it existed when the universe was even younger. This suggests that massive black holes formed rapidly and routinely in the early universe. It wasn't rare. It wasn't a fluke. It was regular. We're literally watching the growth of cosmic structures in real time through these quasars. We're not just seeing snapshots of the universe at different ages. We're seeing the actual process of how the universe organized itself on the grandest scales. And here's what connects this to you right now. The very atoms that make up your body were forged in the cores of stars. Those stars were born in galaxies. And those galaxies grew around supermassive black holes like TON 618. The gravitational influence of black holes shaped the development of galaxies, which shaped the development of star systems, which created the conditions for planets, which allowed life to emerge. Without TON 618 and black holes like it, the structure of the universe would be fundamentally different. You might not exist. TON 618 is about 18 billion light-years away. That's so far that even our most powerful telescopes can only detect its light, the radiation from the material being pulled into the black hole. We can't see the black hole itself. We can't see the event horizon. We can't see the structure of the accretion disk up close. Everything we know about TON 618, we infer from the light it emits and the gravitational effects it has on surrounding space. Let me be clear, science is built on observation, and we cannot directly observe most of what we're telling you about TON 618. We have equations, we have theoretical predictions, we have incredibly sophisticated models based on general relativity, but we don't have direct visual confirmation of the black hole structure. Now, this might make you think, well, how can we be so confident about our claims if we can't see it? The answer is that science doesn't require direct observation if you can measure something's effects. We can't see gravity either, but we can see objects fall. We can't see radiation directly, but we can detect it with instruments. We can't see the curvature of spacetime, but we can measure it through its effects on light and other objects. For TON 618, we measure the brightness of the quasar, which tells us how much energy is being released, the pattern of that light fluctuating over time, which tells us about the structure and rotation of the accretion disk, the redshift of the light, which tells us how fast the universe was expanding when that light was emitted, the gravitational lensing around TON 618, the way its gravity bends light from objects behind it, which tells us about the mass distribution. In 2019, Katie Bouman and the Event Horizon telescope collaboration released the first direct image of a black hole, M87*. This black hole is only about 6.5 billion solar masses, and it's much closer to us than TON 618. In the galaxy M87, the image they produced showed the event horizon outlined by light, the last light that could still escape before falling into the black hole. But TON 618? We can't do this yet. TON 618 is too far away, and the resolution required would be astronomical. However, the success with M87* gives us hope. Perhaps with next-generation telescopes, we might eventually image TON 618 directly. But here's what keeps theoretical physicists up at night. What if our models are wrong? What if TON 618 isn't actually what we think it is? It's possible, though increasingly unlikely, that our understanding of how quasars work is incomplete. It's possible that Ton 618's power comes from something other than a supermassive black hole. Maybe it's a different kind of object entirely that we haven't discovered yet. Science works by constantly testing and refining our models. Right now, the black hole model fits our observations. It's the best explanation we have. But science also has humility built in. We acknowledge what we don't know. This is what makes Ton 618 so fascinating. It's not just a confirmation of what we already understand. It's a challenge to our understanding. It pushes the boundaries of what we think is possible. I want to take a moment to really let this sink in. Not just intellectually, but emotionally. Not just as a fact you can recite, but as something that changes how you see reality. Let me give you some perspective. In your lifetime, assuming you live to about 80 years old, you will experience 29,200 days. In those 29,200 days, you will have countless memories, relationships, achievements, moments of joy and sorrow. Your life will contain universes of meaning to you and those you love. The age of the universe is 13.8 billion years. That's 5 trillion days. Your entire life is about 1/1.7 millionth of the age of the universe. Your lifetime is to the universe's age what a single second is to about 57,000 years. Think of it like this. If the universe's age was a year, you would be born on December 31st at 11 hours 58 minutes and 43 seconds p.m. and you would die at 11 hours 58 minutes and 53 seconds p.m. You would have a 10-second existence in a cosmic calendar. And Ton 618? TON 618 wasn't just created yesterday. TON 618 was already massive and ancient when your universe was born, relative to how old Ton 618 would be today. Now, here's what I need you to understand. This doesn't diminish you. In fact, it does something else entirely. You are not reduced by being small. You are made more miraculous by being small. Your consciousness, your thoughts, your ability to understand these concepts, all of this emerged in a brief flicker of time on a small rock orbiting an average star. And yet, you can comprehend Ton 618. You can look up at the night sky and understand that what you're seeing is genuinely ancient light from genuinely ancient sources. The atoms in your body were created inside stars. The iron in your blood, the calcium in your bones, these were forged in stellar furnaces. You are made of stardust that was processed through stellar cores, scattered by supernova, and collected in a protoplanetary disk that eventually became Earth. You are made from the leftovers of cosmic events so ancient and so powerful that they dwarf anything in recorded human history. When you look at Ton 618 through the lens of modern astronomy, you're looking at a piece of your own history. You're looking at processes that, in a way, made you possible. Carl Sagan said something that still resonates. The cosmos is within us. We are made of star stuff. We are a way for the cosmos to know itself. That's not poetry. That's physics. I want you to sit with this feeling of smallness combined with significance. This feeling of being part of something so vast that your brain struggles to process it. Because in the next section, we're going to answer the biggest question of all. What does it mean that Ton 618 exists? There's a concept in cosmology called the cosmic horizon. It's the edge of what we can see, the boundary beyond which light hasn't had time to reach us since the Big Bang. The observable universe has a radius of about 46.5 billion light years. This is called the cosmic microwave background horizon, and it represents the furthest distance from which we could possibly receive information. TON 618 is 18 billion light years away. It's about 39% of the way to the cosmic horizon. It's in the ancient universe, the universe as it was when it was young and still forming its large-scale structure. But here's what keeps cosmologists awake. We don't know what lies beyond 46.5 billion light years. There's a fundamental limit to what we can observe, not because the universe ends there, but because light hasn't had time to travel from beyond that distance. Alan Guth and Andre Linde, who developed the theory of cosmic inflation in the 1980s, showed that the universe likely extends far, far beyond what we can observe. Inflation predicts that the universe is likely orders of magnitude larger than the observable universe. It's like we're standing in a small lit space, and the room around us is vast and dark and full of possibilities we'll never directly see. Within that infinitely large universe, how many Ton 618s exist? How many supermassive black holes? How many galaxies, stars, and planets? The number is not just large. The number is incomprehensible. And here's where things get philosophical. If the universe is truly infinite, or near infinite, then statistical probability suggests some wild things. It means there's likely an exact duplicate of Earth somewhere in the universe. A planet with the exact same configuration of atoms, with a version of you living through this exact moment, reading these exact thoughts. It means there are probably Earth-like planets with life on them, probably intelligent life, probably civilizations. And yet, we haven't detected any of them. This is called the Fermi paradox, posed by physicist Enrico Fermi. Where is everybody? If the universe is so large, if there are so many opportunities for life to form, why don't we see evidence of it? Why haven't aliens contacted us? One answer comes from the great filter theory. Maybe life is extremely rare. Maybe intelligence is even rarer. Maybe civilizations tend to destroy themselves before they can spread across the cosmos. Another answer. Maybe intelligent civilizations are spread so far apart that they never encounter each other. A third answer. Maybe they're out there, and they're watching us right now, waiting for us to mature before making contact. A fourth answer. Maybe the universe is indeed vast, but communication across such distances is essentially impossible, or so costly that no civilization bothers trying. TON 618 exists in a universe that might be filled with civilizations, or might be populated only by us and microbes on distant planets. We genuinely don't know. And here's what's profound. Ton 618 shaped the early universe. Black holes shaped galaxy formation. Galaxy formation made stars. Stars created the conditions for planets. Planets allowed life to emerge. If Ton 618 had never formed, the universe would have organized differently. Galaxies might not have formed at all, or they would have formed in completely different configurations. And without galaxies, without the specific distribution of matter that resulted, you might not exist. TON 618 is not just a cosmic curiosity. TON 618 is part of the causal chain that led to your existence. We've talked about what we know about Ton 618, but let's talk about what we don't know. And what we don't know is actually more exciting than what we do. First question, is Ton 618 still growing? We observe it as it was 18 billion years ago. But what does Ton 618 look like now? Is it more massive? Is it still actively feeding? Or has it entered a dormant phase? We don't know. Second question, what's actually at the center of Ton 618? At the singularity, where all that mass is concentrated, what happens? Does gravity break down completely? Does space-time become quantum foam? Is there another universe on the other side? We don't know. Third question, could there be a bigger black hole than Ton 618 that we haven't discovered yet? We discovered Holmberg 15A, which might be larger. What if there's something even bigger lurking in the distant universe? We don't know. In the next 10 to 20 years, several developments will revolutionize our understanding. The James Webb Space Telescope, launched in 2021, is already observing the most distant quasars and black holes ever seen. Astronomers like Roger Blandford and Ramesh Narayan continue to develop more sophisticated models of how black holes feed and grow. The Event Horizon Telescope, which took the picture of M87*, is being upgraded. In about 15 years, it might have the resolution to directly image TON 618's event horizon. Imagine seeing the black hole itself, not through inference, but with your own eyes through telescopes. Gravitational wave detectors like LIGO are becoming increasingly sensitive. If there are black hole mergers in distant galaxies, we'll detect them. And those mergers will tell us about black hole growth. Here's something that's going to blow your mind. Some physicists have proposed that black holes might be wormholes, a passage through spacetime connecting two distant regions. Physicist Juan Maldacena and Leonard Susskind proposed the E=EPR conjecture, suggesting that Einstein-Rosen bridges, wormholes, are equivalent to entangled quantum particles. If this is true, and it's still highly speculative, then TON 618 might not just be a one-way passage to destruction. It might be a tunnel to somewhere else, somewhere that defies our understanding of space and time. Probably not, based on current evidence. But we genuinely don't know. The thing about TON 618 is that it represents a frontier. It's the edge of what we can see, what we can measure, what we can understand. And frontiers, by definition, are where the biggest discoveries happen. In the next section, we're going to bring all of this together. We're going to talk about what TON 618 means for you, for humanity, and for our future in a universe filled with objects like TON 618. When I first learned about TON 618, I didn't just learn about a black hole. I experienced something like vertigo, that sense of the ground dropping beneath you, that moment when your sense of scale and perspective suddenly shifts. And I think that's the right response. I think that's what TON 618 is trying to teach us. For most of human history, we thought we were at the center of the universe. The sun, the stars, everything revolved around us. Then Copernicus showed us we're not at the center. Hubble showed us we're in a galaxy among billions. Then we realized billions isn't even the right word anymore. We now think there are trillions of galaxies. And TON 618? TON 618 is showing us that even within those inconceivably vast structures, there are individual objects so massive, so powerful, so transformative that they dwarf the scale of everything else. But here's what I want you to really understand. This doesn't make you small in a way that diminishes you. It makes you significant in a way that should awe you. Think about this. You are a conscious, thinking being. You have subjective experience. You can feel wonder. You can love. You can create meaning. You can understand the universe. And the universe is giving you TON 618. The universe is saying, look at this. Look at what I'm capable of. The universe is showing you its majesty, and you have the cognitive architecture to appreciate it. That's rare. Probably extraordinarily rare. You might be looking at a black hole and understanding it while nearly every other creature on Earth, and likely most creatures in the universe, cannot. Think of it like this. Imagine a single ant, just one ant, had suddenly evolved the ability to understand human language and perspective. That ant, looking at human civilization, would see buildings that stretch toward the sky, cities that sprawl for kilometers, machines that move faster than the ant can run. To the ant, human civilization would be TON 618 incomprehensibly vast. But the ant could still understand it. The ant could still grasp the concepts. The ant could still feel awe. That ant wouldn't be diminished by understanding human civilization. That ant would be elevated. That ant would have transcended its normal existence and touched something greater. That's you. You're that ant. And TON 618 is human civilization. And your mind is the bridge between them. Here's what I want you to carry forward. Every moment of your life is happening in a universe shaped by TON 618. The laws of physics that allow you to exist were refined in the presence of objects like TON 618. The Matter that makes up your body was scattered through space by processes that Ton 618 and its kind initiated. You are, in a very real sense, a child of Ton 618. Your existence is downstream from its existence. And Ton 618 isn't thinking about you. TON 618 isn't conscious. It's not aware. It's just physics, gravity, space-time, the structure of reality. It's indifferent to your existence. And that's actually beautiful, in a way. That's actually profound. You're deriving meaning and wonder from something that doesn't know you exist. You're connecting with the universe on a level that transcends the need for connection to be reciprocated. That's what science gives us. That's what cosmology gives us. That's what Ton 618 gives us. Not answers, wonder. Think about where humanity is. We're at a stage where we can build instruments that detect the light of black holes 18 billion light years away. We can translate that light into numbers. We can convert those numbers into equations. And those equations describe reality. We're also at a stage where we have climate change, disease, poverty, conflict. We have real problems that demand our attention and resources. And yet, we still choose to look up. We still choose to build telescopes. We still choose to wonder. That's not a waste. That's not a luxury we can't afford. That's a fundamental part of what makes us human. That's how we stay connected to something bigger than our immediate problems. So here's what I want you to do. Tonight, look up at the sky. Somewhere in that sky, if your eyes were powerful enough, you could see Ton 618. You could see a black hole so massive that it warps reality itself. And as you're looking, remember, you are made of atoms forged in stellar cores. You are part of a chain of causation that stretches back to the very beginning. You are matter that learned to think. You are the universe knowing itself. And if Ton 618, an object so massive, so powerful, so extreme that it breaks our intuition and defies our imagination, if Ton 618 is just one of countless such objects scattered throughout an infinite universe, then imagine what else is out there. Imagine what we haven't discovered yet. Imagine what mysteries are waiting at the edge of our telescopes, calling us to extend further, to understand more, to push the boundaries of human knowledge. That's the gift Ton 618 gives us. Not just the object itself, but the promise of everything we haven't yet discovered. You started this video thinking Ton 618 was about scale. And in a way, it is. But it's also about time. It's about space. It's about gravity and light and the fundamental nature of reality. It's about the fact that you, a brief collection of atoms that happen to organize themselves into consciousness, can comprehend something so vast, so ancient, so incomprehensibly massive. That's the real miracle. That's what will change you if you let it. I hope this video did more than just teach you about a black hole. I hope it shifted something in how you see the universe, how you understand your place in it, how you feel about existence itself. Because that's what Ton 618 does. It shifts you. It reorients you. It reminds you that the universe is far stranger, far more beautiful, and far more awe-inspiring than we ever imagined. So I'm asking you one more time, drop a comment below. Let me know where you are in the world. What country are you in? What time is it there? And more importantly, how did this video make you feel? Did Ton 618 blow your mind? Did it shift your perspective? I read every single comment, and I'm building a community of cosmic explorers. People who look up, people who wonder, people who feel that vertigo of scale and embrace it instead of running from it. If you did feel that shift, hit the subscribe button. Turn on notifications. Because we've got so much more to explore together. There are mysteries we haven't touched yet. There are questions that will break your brain in the best possible way. There are revelations waiting at the edge of what we know. And you're not going to find them watching doom scroll content or getting lost in the trivial. You're going to find them here, exploring the cosmos with me. Thank you for spending 230 minutes of your finite life understanding something that stretches across billions of years and billions of kilometers. That's not time wasted. That's time invested in transcendence. You are the universe knowing itself. And TON 618 is just the beginning. But wait, I know what some of you are thinking. You're thinking, okay, so TON 618 exists. So what? What does this actually do? How does it affect the universe right now? And that's the perfect question. Because TON 618 isn't just a static object floating in space. It's actively reshaping reality around it. Let me show you what I mean. Right now, at this moment, TON 618 is consuming material. Gas clouds, stellar remnants, maybe entire stars are being pulled into its gravitational embrace. And as they fall, they accelerate. They heat up. They emit radiation. That radiation doesn't just stay near TON 618. It spreads out. It travels. And when it reaches the surrounding galaxy, the host galaxy that contains TON 618, it fundamentally alters what happens there. Here's what will blow your mind. The radiation and jets from TON 618 can prevent star formation in its galaxy. When TON 618 is actively feeding, it's so bright, so energetic, that it heats the gas in the surrounding galaxy to millions of degrees. At those temperatures, gas can't cool down and collapse to form stars. It's like TON 618 is saying to the galaxy, I'm going to use all the available material for myself, and you're going to wait. This is called a GN feedback active galactic nuclei feedback. And it's one of the most important processes in understanding how galaxies evolve. Think of it like this. Imagine a city where someone is running an enormous factory right in the center. The factory is so big, so power-hungry, that it uses up all the electricity in the city. All the other people have to wait for their power. The factory controls the city's destiny. That's TON 618. It's not just sitting there being massive. It's actively controlling the evolution of an entire galaxy of billions of stars. This means that TON 618 shaped not just its own structure, but the structure of billions of stars around it. It determined which stars would form, which wouldn't. It shaped the destiny of that entire galactic system. And we can't even see the galaxy that TON 618 lives in very clearly. It's so far away, so ancient, that the light from the regular stars is drowned out by the brightness of TON 618's quasar. The galaxy becomes invisible. It's like trying to see a candle next to a nuclear explosion. So we only know TON 618 exists because of its power. Everything else around it becomes irrelevant in the presence of that much gravitational and energetic dominance. This makes you think about power hierarchies in the universe. It makes you think about dominance and control. It makes you realize that TON 618 doesn't ask permission to reshape the galaxy around it. It just does it. Gravity doesn't negotiate. And that's actually important for us to understand. Because in our universe, the strongest forces get to shape reality for everyone else. The densest object, the black hole, determines the fate of everything around it. There's a metaphorical lesson there about power and structure that goes beyond just physics. Now, TON 618 isn't floating alone in an empty void. It's part of a larger structure. It's part of a galaxy. That galaxy is part of a galactic cluster. That cluster is part of a supercluster. And all of this is connected by something called the cosmic web. The cosmic web is literally what it sounds like, a web-like structure of galaxies, filaments, and voids that fills the entire universe. Galaxies are arranged along filaments of dark matter, like beads on strings. Between these filaments are enormous voids regions of relative emptiness. TON 618 is a particularly bright node in this cosmic web. It's like a lighthouse in the darkness. And that brightness tells us something important. It tells us that the early universe wasn't uniform. It had regions of greater and lesser density, and those density variations grew over time. In the 1980s and 1990s, cosmologists like Joseph Silk and James Gunn developed models of how the cosmic web formed. They showed that small density variations in the early universe quantum, fluctuations blown up to cosmic scale by inflation, would grow over time through gravity, eventually forming galaxies, clusters, and the filament structure we see today. But TON 618 existed in the early universe when that web was still forming. TON 618 was formed from the densest region of its proto-galaxy. It was the gravitational anchor around which galaxies coalesced. Think of it like this. Imagine the early universe as a slightly lumpy cosmic dough. TON 618 forms in one of the lumps. That lump becomes the densest spot, and everything around it is pulled toward it. But as it gets denser, it starts pushing back the energy from matter falling in heats, everything around it, counteracting gravity. It reaches an equilibrium, and the galaxy forms around the black hole. TON 618 is the yeast in cosmic dough. It's the seed crystal around which the larger structure crystallizes. And here's what gets really strange. Because TON 618 is so luminous, we can actually use it as a tool to study the universe between us and it. The light from TON 618 passes through billions of light years of space and billions of years of time. And in that journey, the light encounters intergalactic dust, intergalactic gas, and the gravitational fields of matter along the way. The light bends slightly. It gets absorbed slightly. The colors get distorted. By studying that distortion, astronomers can essentially read the story of the universe's evolution, written in the light of TON 618. They can figure out how much dust there was at various epochs. They can measure the density of the intergalactic medium. They can track the distribution of metals, which in astronomy includes everything heavier than helium. TON 618 is a cosmic flashlight illuminating the history of the universe. Here's a question that might seem abstract, but it's actually crucial to understanding the future. What happens when TON 618 runs out of material to consume? Right now, TON 618 is actively feeding, but there's only so much material in its host galaxy and its immediate surroundings. Eventually, maybe in a few billion years, maybe in a few trillion years, TON 618 will consume everything nearby. The quasar will turn off. The jets will shut down. The radiation will cease. TON 618 will become dormant. And when it does, it won't disappear. It will still be there, still curving spacetime, still exerting gravitational influence, but it will be invisible. It will become one of the countless dark supermassive black holes drifting through the universe, waiting. Some of these dormant black holes might be awakened if another galaxy collides with TON 618's host galaxy. When galaxies collide, material gets disrupted. Some of that material might fall toward the black hole, reigniting the quasar. The black hole comes back to life, but most won't. Most will remain dark. And here's what's profound. The universe was probably much louder when it was young. More quasars, more active galaxies, more radiation. As the universe has aged, the quasars have gradually turned off. The active black holes have consumed what was available and gone dormant. We live in a quieter universe than the early universe, a darker universe, a more mature universe. This is actually a metaphor for aging. The universe is growing old. Eventually, in trillions of years, the last stars will burn out. The last black holes will evaporate through Hawking radiation. The universe will reach heat death, a state where there's no energy gradients, no structure, no change. But we're not there yet. We're in the middle of the story. We're in the era where stars are still forming, though less frequently than before, where black holes are still feeding, though mostly dormant, where structure still exists and changes. TON 618 is a relic from a younger, more energetic universe. It's a window into how much more dramatic things were in the early cosmos. I want to introduce you to another layer of complexity that most people don't think about when discussing black holes: rotation. All black holes rotate, and the speed of that rotation matters enormously. A non-rotating black hole is described by the Schwarzschild solution to Einstein's equations. This is the simplest type of black hole. But most black holes are rotating, described by the Kerr solution that Roy Kerr developed in 1963. When a black hole rotates, it does something extraordinary. It drags space-time around with it. The frame-dragging effect, as it's called, means that the very fabric of space-time is spinning around the black hole. Think of it like this. Imagine space is honey. A non-rotating black hole is a sphere in the honey. But a rotating black hole is a sphere that's spinning, and as it spins, it drags the honey around it. The honey doesn't want to spin, but the sphere forces it to. Roger Penrose, a Nobel Prize-winning physicist, showed in 1969 that you could theoretically extract energy from a rotating black hole using something called the Penrose process. If you could navigate the ergosphere, the region outside the event horizon where space-time is being dragged, you could extract rotational energy and use it to power a spacecraft or a civilization. This is purely theoretical. We can't actually do this. The engineering is impossible with any technology we can imagine. But mathematically, it's possible. Now, here's the question. How fast does TON 618 spin? We don't know for certain. But some calculations suggest that massive black holes like TON 618 might spin at relativistic speeds, approaching the speed of light at their equators. If TON 618 is spinning at near maximum speed, then the frame-dragging effect is enormous. The space-time around it is being twisted at incredible speeds. Light itself gets dragged around. This actually affects how we observe quasars. The shape of the jets depends on the spin rate of the black hole. The brightness depends on the spin. The entire appearance of the quasar is influenced by how fast TON 618 is rotating. And we still can't measure this directly. We can only infer it from the pattern of light and radiation. One of the most mind-blowing developments in recent astrophysics is that we can now simulate black holes like TON 618 using supercomputers. These simulations are extraordinarily complex. They have to account for general relativity, which curves space-time, magnetohydrodynamics, the physics of charged plasma, and quantum effects. They have to track the motion of billions of particles across regions that are light years across. But we can do it. And when we do, we learn things. In 2019, the Event Horizon Telescope collaboration didn't just take a picture of M87's black hole. They also ran detailed simulations of what the image should look like based on different theoretical models. By comparing the simulations to the actual image, they could test their models and rule out some theories. We could do the same thing with TON 618 if we could image it directly. These simulations show us something astonishing. The structure around a black hole is far more complex than we imagined. The accretion disk isn't uniform. There are hot spots. There are magnetic tornadoes. There are jets that are twisted and precessing, wobbling like a spinning top. The structure changes over time. What we observe at any given moment is just a snapshot of something that's constantly evolving. This means that TON 618 isn't a static object. It's a dynamic system. It's churning. It's evolving. It's alive in the sense that it's changing constantly. And that changes how we think about it. It's not a monument. It's a process. Now, let me bring this back to you. Back to the present moment. Back to why this matters for your life, your future, and the future of humanity. Here's something nobody talks about. Black holes like TON 618 might be the future of civilization. Think about it. A black hole is the ultimate power source. It's an object that converts mass directly into energy through gravitational processes. The efficiency is astronomical, pun intended. A sufficiently advanced civilization could potentially harness a black hole to power themselves essentially forever. Not by doing the Penrose process, which is likely impossible, but by other means we haven't thought of yet. Imagine a civilization that has survived for 1 billion years. They've mastered space travel, they've mastered physics, they've solved every problem we can think of. What would they do next? They might build a Dyson sphere around a black hole to capture all the radiation from matter falling into it. They might create artificial accretion disks by feeding material to the black hole in controlled ways, powering massive computational substrates. They might even use black holes for computation. Some theoretical models suggest that the surface area of a black hole is related to how much information it can store and process. A civilization based around a black hole like TON 618 would be so powerful, so capable, that we'd have no way to even recognize it from our current perspective. And this brings us back to the Fermi paradox. Where is everybody? Maybe they're around black holes we haven't discovered yet. Maybe they're using them to power civilizations so advanced that they don't even bother with the visible universe anymore. Maybe TON 618 already has civilizations around it. Maybe it has always had them. We have no way of knowing. But here's what will truly blow your mind. We might be observing TON 618 at the exact moment when a civilization around it is making first contact with other civilizations. We might be looking at the light from TON 618 from a time when something extraordinary is happening in that system. But because the light takes 18 billion years to reach us, we're seeing ancient light. By the time it reaches us, whatever was happening is 18 billion years in the past. We're looking at ghost light from a ghost epoch. TON 618 represents the boundary of human knowledge and human imagination. It's real, it's measurable, and yet it's so extreme that it pushes against the limits of what we can understand. And that's okay. That's beautiful, actually. The fact that there are still mysteries, the fact that there are still frontiers, the fact that our understanding hasn't reached its limit. Because as long as there are mysteries, there's reason to keep looking. There's reason to keep wondering. There's reason to build bigger telescopes and smarter instruments. There's reason to imagine what might be out there. TON 618 isn't just about a black hole. It's about the human spirit. It's about our capacity to extend our understanding beyond our immediate experience and touch something genuinely vast and genuinely real. You came into this video thinking you were going to learn about size. You're leaving having touched something deeper, the nature of reality itself, the power of human cognition, the profound beauty of the universe. And that transformation? That's what science is really about.